we are talking about energy. Yes? If you're talking polymorphism, you are talking about energy. And if you look to the lattice energies of polymorphs, here, once again, this is here a table, a figure of lattice energies of Roy. Yeah, going back, here, a little bit better. And this is the temperature, and this is so the difference about the free energy minus the energy of epsilon. So this is a fixed, system is fixed to epsilon, the energy, free energy of epsilon. Looking to the differences. This is epsilon here, no? This is the value is O. What you see, two things you see. One thing is you see the difference from the temperature, yeah, very nicely. And the second thing is, for example, look here, to the energies, the lattice energies of the ON and OP lattice. You will see this is a very tiny, extremely tiny difference. No? And we are talking about, this is the range, we are talking of kilojoule per mole. You see there's a difference about what shall I say 0.1 kilojoule maybe, not more. Or on the other side, if you look for a big difference, let's have a look, what shall I have here? OP, here ON is round about, I would say, 0.35. And here, if we compare, if we look to the difference epsilon to ON at around about 120 degrees, the difference is 0.3, less than 0.4 kilojoule. You see, this is extremely slight differences in the energy of polymorphs. And which should be general mention if you try to crystallize polymorphs. And this is the reason, with slightly difference, it is sometimes very easy to switch from one polymorph to the other polymorph. If you find a method, a tool, to manipulate, to tune with energies. You know? So, we're talking about thermodynamic and kinetic stability if we are talking about polymorphism. First, what is the thermodynamic stable? This is the global energy minimum form. No? This is the form which you will find the global energy minimum. This is thermodynamic. All other forms, or the other polymorphs, but it depends how many polymorphs you have, are called metastable forms. We have local minimum. No? And the metastable polymorph is thermodynamically unstable, but it has its own existence. Yes. When it depends on temperature, pressure, and it depends about the rate, how quickly or slow it can be transformed to the most stable polymorph form. And so that is the reason here, the question of thermodynamic and kinetic stability. Talking about polymorphism investigation, we are talking about, or this is an interplay. Yeah? This is a competition about kinetic and thermodynamic control of a crystallization process. No? Thermodynamic means how far relative stabilities and transformations that can occur between the forms. And kinetic means how fast the time needed for the transformation to reach equilibrium. Playing with these two types. Well, you can see this very nicely. I think each student have seen something like this, the reaction coordinate with free energy, And well, you have two different forms. We're starting here when you have two possibilities. This is the form here. When I'm starting here, G1. G1 has higher energy in transition state, but forming this more stable polymorph. No? On the other side, we have a lower transition state here, or the barrier, lower transition barrier, I would say, and then you can find the kinetic or the metastable form. No? Okay, and this is the plane here. This is a region we can play. Okay. And going back to this here, very nicely, there's a very old rule, and it fits fascinating good in crystal engineering. This is called Ostwald rule. That is, when we leave an unstable system state, for example, solution, the system does not seek out the most stable form, but rather the nearest metastable state which can be reached with least loss of free energy. Step by step going down. Ostwald's rule of stage slide. And this could be sometimes our task, to stabilize one of these metastable stages. Okay. But we must have a look. We must have a look on the systems. So we must talk about some other parameters of crystallization. For example, we have two different forms, polymorph forms. I always said one is thermodynamic stable, and I said the other is, all other are metastable. This is not exactly true. I said the metastable form can exist, can be obtained in special ranges of temperature pressure. This is important. Well, we have two different forms. We have a monotropic polymorphic systems. You have a free energy with a temperature. And independent of the temperature, always one form is more stable in contrast to the other form. Of monotropic system. The other form is called anisotropic system. And this is exactly what I said. Depending on the parameters, temperature, metastable could also be stable. Well, we have one. This is here. Have a look at the curve. B is going here and A is going here. You see, in this case, the A at low temperature, polymorph form A is stable, and at higher temperature, polymorph B is the stable form. And there's a transition temperature, there's one point, transition temperature, at this point both polymorphs has the same stability, or have the same free energy. Well, once again, anisotropic system, each anisotrope has its own temperature range of stability. Okay. So, if your task is to obtain crystals or polymorphs and so on, one of the first step is looking to the temperature stability. So the stability of a polymers depending on the temperature, to decide if you have an anisotropic system or a monotropic system. And this is important for the next experiments, your investigations. Okay. Next point. If you're talking about polymorphism, very often we must talk about involved intermolecular interactions to stabilize one of the desired polymorphs. So there are, I would say, three different classes of intermolecular interaction polymorphs. There is a very thumb rule about all these, talking about those classes. We can say we have the same functional group, and the same syntron, but difference in overall packing. For example, if you look here, so resothenol, we have two resothenol, two hydroxy groups here, and you will see interaction of a hydroxy group with a neighboring hydroxy group. Here's one hydroxy group, the neighboring one, and so on, and so on, and so on. So each compound molecule had interaction 2 times. I had interaction here, kind of interaction. And in this case also, but you see very nicely, in this case I would say you have a 4-membered ring of molecules, tetrameric unit. And in this case you have, you can say you have dimers if you want, or you can say you have a chain burden. You see the difference in the overall packing. The second type is we have the same functional group and the same syntron, but not always the same occurrence, multiple occurrence of these groups in different and distinctive molecular locations. Have a look. We are looking to pyrrocene amide. This is on a backbone with 2 nitrogen inside of the backbone, aromatic backbone. We have here the amide group that's attached. So if we look into the polymorphs, when you see here NH, always, so the amide group is not involved, yes. Looking only to here the nitrogen, the amino group, which dominate with packing, the polymorphs, but you see the difference of these 3 polymorphs. Always the same pattern, but difference overall. And the last one is if you have different syntrons. In this case here, we are talking the same syntrons, and in this case we have different syntrons. Different syntrons leads to different crystal packing. For example, if we have a dihydroxy benzoic acid. See it here. This is the acid function or acid motif, and we have a dihydroxy group. And you see here the differences. Here, in one case, here the hydroxy group, and the carboxylic group is here forming here. And in this case here we have a hydrogen bond to the neighboring, something like dimer and a catamer function, something like this. There's no catamer, it's only related a little bit, similar, not more, similar to catamer function, more dimeric pattern. Okay. Let's talk about the next point. Let's talk about characterization of polymorphs. There are several methods well known suitable for characterization. First, let's talk about thermal effects, differential scanning calorimetry. Yes, you have a compound and look to the behavior of a crystallization compound and melting compound. And this is the energy. So we have here the temperature and you have the energy. And what you're looking is the crystallization energy, the energy, and you look into the melting point. Both are related in both cases. Very nicely, you can have a look on the energy. This is a typical system. It crystallizes at lower temperature and it will melt at higher temperature. In a typical way, you repeat the cycles several times. This picture I've shown you in the earlier slide. This is the case, for example, if you have polymorphic behavior, or this is indication, a hint that's going on something. So it's not easy. This is not a typical picture you would expect it, or a typical result. You have a crystallization temperature, a melting point, and additionally, once again, you have a second melting point, and then a second crystallization temperature. Well, in this case, it was obtained in crystallization of the polymorphs. Next point is thinking about thermal methods to distinguish, control, prove polymorph is hot stage microscopy. Very nice, very simple. What you need is a microscope. All you need hot stage. Heizplatte. No? Not more. Yes? What you are doing is you place your crystals on this hot stage, and when you can play with the temperature, increase the temperature, and after increase the temperature to decrease the temperature, and you can very nicely observe by this microscope the crystallization and melting behavior of your system. Nice example. Here, this is the picture. You can get it. This is one compound. We have on the left side called A. And on the other side, we have component B. Okay, you place it on this hot stage, and when you increase the temperature, you see this melting, and then you can crystallize, and when we decrease the temperature. What you see is now, here in the middle, and the border between A and B, you see what a new compound, a new crystal form appears. Very nice, you see it here. C. And additionally, you see it here at the border of B. You see a fourth zone, and this is the form of eutectic mixture of the co-crystal and the form B. This is a very nicely snapshot, which help you to control and to visualize the polymorphic behavior of substance. No? And this was thermic control. The next thing is, this is the best way in general to characterize and analyze the crystals. Well, single crystal diffraction, and the information you will get is the cell constants first, then you will get the molecular structure, and then you get molecular arrangement. Yes, a lot of information. But it's not always necessary. Yes, single crystal determination. Another point or another method which is very useful, very extremely useful for polymorphic studies is powder diffraction. In this case, you will get information about phase which is present. No? Form, you can say phases, the crystalline entity, the polymorphic forms. So compound A, is it present, or compound B is present, or a mixture of both, or co-crystals. So this is phase present. No? You will get it from the reflection positions. You can get the quantity, concentration a little bit, no? Depending on the reflection area. And you can get information of, for example, if there are amorphous compounds present. Here's an example. These are two polymorphs of co-crystals. No? Carbamazepine, saharin co-crystal. Look to, this is the intensity, and this is the angle. The angle for reflection. This is a reflection. The measured reflection depending on the angle. See it here, the intensity. And I think it's very easy to see that there are several reflections from form A form 1 which could not observable in this red line form 2. And this is always an indication we have two different entities. It must not be directly polymorphs, but these two compounds are not the same, which are not the same compounds. No? Well, it could be, I don't know, polymorphic form, and co-crystal, hydrated, and so on, or might be a side product, whatever you want. No? But definitely form 2 or with power diffraction from this red one is not the same like the power diffraction of the black one here. This is information. And this could be sometimes still enough in polymorphic investigations. It's you can get it very quickly, very rapidly, and you can directly say, okay, I get the same, stop this experiment, or, well, okay, this could be an indication there's something going on. Let's have a closer look. This is what you can get, this information that helps you in investigations. How can you control polymorphic formations? Well, this is a huge topic, fascinating great field of different methods. I will show you now some very easy factors. One is, solvent effects. I have shown you acridine, yes, and these are the power diffraction from acridine. Once again, very nice. You can use power diffraction to distinguish between all these forms, 2, 3, 4, 5, 6, and so on. You can get all this polymorphic form only by playing by crystallization acridine from different solvents, or same solvents, a little bit differences in crystallization behaviors. Temperature. For example, by playing with temperature, you can get different polymorphs. See it here, pentafluophenol at ambient temperature, yes, we get with high temperature and a little bit lower temperature. It's not so far, this is only 23 degrees, not so much, and there's not so huge difference. It's still enough to get a new polymorph, secondly kinetic controlled. Or pressure. Crystallization under ambient temperature or crystallization of higher temperature. This is in the case of bromochlorofluoroacetic acid. In the case of 0.59 gigapascal, you will see this catenary form. And in the case of you increase the pressure 1.37 gigapascal, gigapascal, don't forget, you will get this diagram. Very nicely shown by Katrushiak. So, I will show you why, from my point of view, polymorphism is so fascinating and sometimes really mystery. This is an example, it's very well known, it's a long time, this is from the pharmaceutical industry application, and this is tetraacetyl ribofuranose, you see it here, and here are the 4 acetyl groups attached to the ring, and this is form 1. This form 1 was observed at the beginning, first synthesis of this quark, and it has a melting point around about 60 degrees, and it was possible to repeat this synthesis, and I got several times this form 1. and suddenly we got form 2. Yeah. The same preparation procedure. We didn't change anything. And suddenly we got form 2. Form 2 has a little bit higher melting point, 85 degree, and you see this is a conformational polymorph. Very nice. You see here the difference and orientation here of acetyl group. No? Yeah, that's all. Okay. Strange, really strange was we never got form 1. After appearance of form 2, the crew, the team, were not able to prepare form 1 again in this lab. We always got obtained form 2. So what I have done, they spoke with colleagues and colleagues in other part of the country, for example, west and east coast of USA, and the colleagues prepared in their lab form 1, successful, no problem, put it in a closed vessel, transport it to the first lab, where I open the tube and spontaneously form 1 convert to form 2. Yes, this is really amazing. What's the reason? The reason is there's only some crystal nucleus, nearly nothing, is in the atmosphere, in the air, in the lab, of the first lab. And this is still enough. There's this like seeding effect. Still enough, there's this seeding of nucleus of form 2 directly, spontaneously switch the whole batch from form 1 to form 2. And in this case, this situation, we talk about disappearing polymorph. Form 1 as a disappearing polymorph. Yes. And well, okay, it's this mystery. Yeah? On the other side, this is a huge problem in the pharmaceutical industry, definitely. And it sometimes happens, not very often, but sometimes it really happens that the presence of a thermodynamic, more stable form lead to the situation that it's not possible to obtain the kinetic form once again. Disappearing polymorphs. This is really a mystery form. At the end of this session, we will talk about something nice. We will talk about chocolate. Yes? Well, you know, this is chocolate. This one is an eatable form of chocolate. And if you store the chocolate a longer time in the cabinet at a high temperature, 1 month, 2 months, and so on, after the summer, look into the cabinet, in the cabinet, when we will see the chocolate has changed. And you know, everybody have seen something like this. Okay. There are 6 polymorphs known about chocolates, or 6 forms. I would say 6 forms. No? 1, 2, 3, 4, 5, 6. And you see the difference is the melting point. Rapidly cooling, you will get rapidly cooling from a melt. You will get a form with 70 degree melting. It's below room temperature. And if you control melt, yes, with 2 degree per minute, you will get form 2. And crystallization between 5 and 10 degree, crystallization range between 16 and 21 degree, form 3, form 4. 5 you will get by slow crystallization, and 6, this is what I said, after several months at room temperature. Yeah? And this is a gray, something like grainy, dull surface. And look to the temperature, it doesn't melt in the mouth. No? It's nearly the same temperature like our body temperature. Well, for us interesting, the eatable form is form 5. This is form 5. A thermodynamic stable form is form 6. If you want your desired form, it's not so easy to get it. First you melt your compound at 50 degree. When you're cooling down, gradient to 22 degree, 1 degree per minute, and then you hold it for several minutes, because you need sufficient number of crystal nuclei. When you warm up at 31 degree, form 4 melts. You remember different melting points of the forms. And when you're cooling slow, when you will get the desired product. This is chocolate. And if you look to chocolate, you will see one of the major ingredients of this compound is this glycerol. This is the main function, one of the major fractions of cacao butter, this glycerol. And from this glycerol, different polymorphs are also well known. And if you look to the crystal structure, well, you will see the form 5 could be crystallized. They were able to determine the crystal structure. The molecular structure of the form 5 looks like here. Have a look. You have 3 changes, S1, S3, and the second change is this one. And this is the node, you can say, and in this node the 3 changes are linked. And here, if you look C9, C10, this is a double bond. Okay? This is the crystal packing of form 5. Once again, you see the change with the blue here, blue signed region is the region of the double bond. This is the difference here. The neighboring double bonds are here. This is the first thing what you see. And the second thing what you directly see, you have voids. Here we have voids, here, voids. This is not the optimized pact. You can directly see. So this is really the experimental observation of form 5. And if you compare the experimental crystal structure with the postulated calculated form, you can think about the differences. Explanation of the difference of different forms of glycerol. Well, first thing is, as I talk about this carbon-carbon double bond, you would expect that you have pp interactions, yes, of a neighboring double bonds. And you see in this case there's a big difference. It's not really neighboring. Second thing is the orientation. If you look to orientation of the changes, you will see that there's a difference. There are angles between this here. There's an angle between the changes and optimized. The orientation of the change is not optimized. You would expect that you have a really parallel arrangement of the changes. And the last point is, this is regarding with voids. If you look to the angle, torsion angle, yes, there's a torsion angle with 4 atoms, you would expect optimized is nearly small difference. No? With a small difference means a close packing. In this case, it is not optimized, the differences. Well, and this is the end of a presentation, this is the end of this topic, polymorphism. The last example very nearly shows you how investigation could help to explain features, phenomenon we can observe, not only in very special scientific questions, also in some things like chocolate. Huh? Okay.